Hello, this is the video for the review collaborative for exam 3. So making the solutions with you here. Let's jump in with number 1. They're asking us to solve for b in the log base b of 4017 equals 7. And the key to this type of equation is to rewrite it as an exponential at first. So you take the base of the log, you raise that to the other side of the equation, which is the 7, and that's equal to whatever was inside the log, which in this case is 4017. So the base to the other side equals what was inside. And when you do that step, you've gotten rid of the logarithm. So now we just need to solve for b, and b is being raised to the 7th power, so we have to undo that. And the way you do that is raise this side to the reciprocal power. Remember that a power to a power you multiply, and 7 times 1/7 would be 1, or b to the first, or just b. So this is going to cancel that exponent off if we do that. So we do that on one side, so to keep things balanced we would have to do that on the other side as well. So we're going to raise both sides to the 1/7, and that will have the effect of canceling the exponents right here. So what's left on the left hand side is just b, and on the right hand side we have 4017 raised to the 1/7. So that's a little bit of a weird way to write that, but that's because that's the way it looks on the graphing calculator. And that is where we're going to go next, because they asked us to round to 3 decimal places. So I'm going to take that 4017 and I'm going to raise that to the 1/7. Very important when you have an exponent that's a fraction that you put that exponent inside of parentheses, otherwise you're only raising to the numerator instead of to the whole fraction. So we'll press enter and then we'll get our approximation. So they said to round to 3 decimal places, so b is approximately 3.272. So that's the answer to that one. And if you wanted to check it, you could go back to this part and raise that to the 7th, because it said b to the 7th was 4017. So we should get 4017, which we do. So that's just a quick check on that. Alright, moving on to problem number 2. A 10-year-old's grandmother invests $1,500 for him in an account that earns 5.3% interest per year. He forgets about the investment and discovers it again 35 years later. How much money would be in the account at that time, and round that to the nearest penny? So whenever you're doing compound interest and you have an initial investment, that's always going to be an exponential growth type of function. So we're going to look for some sort of y equals a times b to the x sort of situation. And the a is always the y-intercept, which should be the starting time or the starting amount. So here we're starting out with $1,500 at time 0. So that would be a equals 1,500. And then you also need to figure out b. And when you're earning interest on money, it's growing. And it's growing at 5.3%. So that is going to be involved in b, but that is not b by itself. In order to have growth in an exponential function, you need to have a base that's bigger than 1. So we need to take a base of 1, which in percentage form would be 100%, and add the growth amount 5.3% to get 105.3%. And that would be the base, only this is in percentage form, and we need to convert it to decimal form. So move the decimal over 2 spots, and we get b equals 1.053. So we've got our coefficient and we've got our base, so we can write our function. And I will write it in function notation, and we're using the variable t here for time probably, since we're talking about 35 years later. So I'll write it as f of t, and then a is 1,500, and the base is 1.053, and the variable is going to be t for time. So again, in order to have growth, you have to have a base bigger than 1. That interest rate is how much bigger than 1 you are. So I did it by adding 5.3% to 100%. You could also do 1 plus the decimal version of 5.3%, and that would get you straight there too. But you have to add on to 1, otherwise you're not going to get that greater than 1 base, which is required for growth. Alright, so there's a function that can now be used to answer the question, which is how much is the investment worth 35 years later. So 35 years, so that's the time. So we would plug that in for t, f of 35 equals 1,500 times 1.053, and if I plug in 35 for t there, then I have to plug 35 for t there also. And then at that point we're ready to go to the calculator. So 1500 times 1.053 and raise that to the 35th power and round that to the nearest penny, which would be 2 decimal places. And we're talking about money in dollars here, so $9,142, and it's a 90 but followed by a 5, so I'd round up there and say 91 cents. So $9,142.91, which would be a nice surprise given that they forgot they had that money in the first place, and now to find out it's worth a lot more than they remembered back on their 10th birthday. Alright, also we've got work kind of scattered around here, so it would be good to box that answer, so I'll go ahead and do that. And then let's move on to problem number 3. They want us to solve 5.3 times 1.8716 raised to the t plus 19.8 equals 307. The key here is to look at the variable and notice that it is the exponent. Anytime your variable is the exponent, you're going to need to use logarithms to solve the equation. But before you can do that, you have to get this base piece by itself. So we have to get rid of the 5.3 and we have to get rid of the 19.8. And if you think about an equation like 5x plus 19 equals 300, you would subtract this first and divide by that second. So we're going to follow that same order when we're working with this exponential. We're trying to get that base by itself, so first we'll subtract 19.8 from both sides. So those cancel. So at that point we are at 5.3 times 1.8716 to the t equals, doing the subtraction on the other side, we get 287.2. So I have that answer available so I can peek at it. Feel free to use your calculator to do that piece. And then we're still trying to get this base by itself, so this part right here by itself. So that means we need to get rid of that 5.3. That is connected by multiplication, so I'll divide by 5.3 so those will cancel. If I do that on the left, I'll do it on the right as well for balance. And then we have 1.8716 raised to the t. And if you divide this part right here, then you would get a decimal and you would round it, and that would bring an error. So rather than doing that, I'm just going to write equals. I'm just going to copy that fraction down to 87.2 slash 5.3. I'm writing it this way because I'm going to go into the calculator pretty soon, and I want to write it in the way it's going to look in the calculator. Alright, so we said on these previous steps we needed to get the base by itself. We've done that now. So at that point you can come in and take a log of both sides. So I take a log of the left and a log of the right. And the reason we do that is log has that special property where if there's an exponent on the inside of the log, you can bring that out front as a multiplier. So we can cross that t off here and move it to the front. And the beauty of doing that is now t is connected to this log as a multiplier rather than as an exponent. And we know how to undo multiplication. We undo it with division. So I'm going to divide both sides here by log of 1.8716, which will cancel this piece, and then the only part that would be left is the t. But if I'm going to do that on the left, I have to do it on the right also. And at that point I have t all by itself. So the exact answer to this problem for how much time is it going to take is t equals the log of 287.2 divided by 5.3 all over the log of 1.8716. Alright, and then we just want to get an approximation for that to 4 decimal places, it says, so we're going to put that in the calculator. The key is these two sets of parentheses, well especially this top one because there's 2 numbers in the log. You have to have that set of parentheses, otherwise you'd only get the log of the first number. Here, that's just for visual purposes. Those parentheses aren't really necessary, but the calculator always does the open for us, so we'll just have to close it. Alright, so let's punch that in. So we have the log of 287.2 divided by 5.3. Once you get both numbers in, then you can close the parentheses so that it's the answer to that division inside the log. And then divided by the other log, which is 1.8716. Round that to 4 decimal places, so that would be about 6.36 9.6, but followed by a 7, so round that up to 9.7. And that's our approximation for t. One thing that's nice on a problem where you've done a lot of messy steps here, subtracting decimals, dividing by decimals, taking logs, something could easily go wrong. So if you want to check that, take this answer, plug that in for t right there, and if it's really the answer, when you work all this out with that number plugged in, you should get 307. So 5.3 times 1.8716 raised to that answer we just got. So you could type it in, or above the negative key it says A and S. If you hit second and A and S, it stores that number with all its decimals that you can see and more beyond the screen, and it plugs it in there. So you're plugging a really precise version of your answer in for t if you do that, and then plus 19.8. And if that answer right there is really the correct answer, when you plug it in here, you'd get 307, which we do. So it's nice to be able to check that. Right now you're watching a video to check your answers. You can't do that during test time, but you could take an answer like that and plug it back in and see if it works. And if you have time, I would suggest that. It can help you catch a mistake. All right, moving on to number 4. The numbers of polio cases in a certain country are shown in the table to the right for various years. Let f of t be the number of polio cases in thousands in the year that is t years since 1980. So the first thing I'm going to do when I look at this table is add a t column. So here's all the years, but let's make a new column for t. We started the clock in 1980, so 1988 is 8 years later. 1992 minus 1980 is 12. 96 minus 80 is 16. 2000 minus 1980 is 20, and so on for 25 and 27. So you want to convert those years to values of t as your first step, and we're eventually going to try and find an exponential equation using our graphing calculator and regression. So we're going to want to put this stuff into the graphing calculator. So those values of t will go into L1, and then these number of polio cases we'll put into L2. So that's the next step. So we bring the calculator in. Let me back up here. So I'd hit the stat button to get my options up. Press the edit choice. My columns are empty. If there had been some numbers in there, remember to highlight the list, clear and down arrow to get rid of those. And then let's type in the new stuff. So 8, 12, 16, 20, 25, and 27 for the inputs, and the outputs over here, 79, 22, 9, 8, 1.9, 0.4. So there's our data, and now we're going to do the regression to get the equation. I like to think about that a little bit, and one thing I want to see is, do I have growth or decay? So as time is going forward, the number of cases of polio is going down. So we have an exponential decay here, so our base should be smaller than 1. All right, so we're going to hit stat and calc, and then arrow way down there to exponential regression, which is 0 on my calculator. And then I'm going to tell it where the data was. The inputs were in L1, the outputs were in L2. It'll show me the format, y equals a times b to the x, and it'll tell me what a and b are. And then we're going to round to whatever they said, which is a lot of decimal places in this case, so 6. And they want function notation where the input is t. So I'm going to say f of t is approximately equal, and then I'm just going to pull these numbers in. So let me slide this over a little bit so we can see both. So for a, 523.91274, said 6 decimal places, right? So 1, 2, 3, 4, 5. The next one's a 2, but followed by a 5, so I'd round that up to a 3. And then times the base, which is right here, 0.7852. It's a 79 for the next 2, but followed by an 8, so I'll round that 79 up to an 80, and then raise to the t. So that's the answer for the regression equation. I'll go ahead and box that. And then just a reminder for you, I got there by doing exponential regression L1, L2. All right, so let's use that equation now to predict the number of polio cases in 2003 and round our answer to the nearest whole number of cases after we convert from thousands. So the first thing is to figure out t. So t is the year they're asking about, 2003, minus the start time, which was 1980. So do that subtraction, we get t equals 23. And now we're just going to plug that into our function. So we want f of 23. A lot of decimals makes it accurate. A lot of decimals also makes it kind of a little bit of a tedious pain to keep writing. The price of accuracy, I suppose. All right, so let's put that in the calculator, see what we get. All right, so we type all that in, and it says to round to the nearest whole number of cases. So you're tempted maybe to round that to 2, but this is in thousands of cases. So if I just wrote it out kind of as is, it's 2.0175545. There's kind of a lot of decimals, but that's not cases, that's thousands of cases. So if I want to get it to the nearest whole number of cases, what I need to do is take what is in the calculator, multiply it by that 1,000, so times 1,000. And now I've mixed that word into the number, and so now that would be gone and it would just be cases. So that would be approximately 2,018 cases if I rounded that 7 up because of the 5. It's easier to do that, I think, if you multiply by the 1,000 and then round. If you round sooner, it's a little more confusing about what spot to round to. All right, let's see what else they have for us in this one. Interpret what the base means in terms of the application. So first of all, the base is the part that has the exponent on it. I guess looking up at the function would be better than here, but same number. So the base is this 0.785280. So as we mentioned earlier, the number of cases has been decreasing, which is good. Polio is a bad thing. We're getting less of it in this country. And that decay in the number of cases is reflected by a base that's smaller than 1. So how quickly it's decaying is a matter of how far away from 1 it is. So what you want to do is take 1 minus this number. So 1 minus b, or 0.785280, is 0.214720. And once you do that subtraction, you're looking at the amount of the decay. So let's go ahead and convert that to a percentage. So we'll move that over 2 spots, and that would be 21.4720%. And that difference between 1 and your base is either the growth or decay percentage, and because the base is below 1, it's a decay percentage. So every year the number of polio cases is decaying or decreases by this 21.4720% from the previous year. So let's write that out. So the key thing there that people often forget to do is take the difference from 1. They just want to kind of look at that number and make it a percentage. But an exponential function grows if this is bigger than 1, and the growth percentage is how much bigger than 1. It's a decay if this number is smaller than 1, and the decay percentage is how much smaller than 1. So you always have to do a subtraction involving 1 and your base to see how far apart they are, and then you use that difference as your percentage of growth or percentage of decay. The other question they want us to interpret, I think, is a little easier. Interpret what the coefficient A means in terms of this application. So that number out front is always the y-intercept, which means it goes with an input of 0. So that would be 0, 523.91. I just copy it all down, 2743. And I left a little bit of space here to think about what the units are. So the 0 would be 0 years since 1980, And this would be the number of cases, and according to the way the original data was, that's in thousands. So this would be thousands of cases. So when we go to interpret it, 0 years since 1980 is 1980. And then this is thousands of cases. So if we take that number, 523.912743, and multiply by 1,000, then it would be just cases. You could do that on the calculator. We could also just move that over 1, 2, 3 spots. So it should be 523,000, 913 cases, rounding this 2 up because of the 7. So this becomes 523,913 cases. So that's all scratch work. I haven't officially interpreted it, so I'll just put that into a sentence. So I'm going to say the model predicts that there were about 523,913 polio cases in 1980. So I just want to point something out. The model predicts isn't always what the truth was, right? So according to this model, it looks like that's how many cases there would have been in 1980. We always have to worry about model breakdown, that when we go outside of the range the years were given, that things won't be exactly perfect. So I'm not making a factual statement here like in 1980 there were this many cases. I'm saying what the model predicts it would have been. And I say the word about because I know models don't give perfect predictions. Plus I had a little bit of rounding in there as well. All right. Okay, moving on to number 5. They want us to simplify this expression. It's got some exponents in it, including some negative ones. So first of all, our kind of first introduction to simplifying was reducing fractions. And the 42 and the 24 have a 6 in common that I'll be able to reduce. So I just want to show that 42 is 6 times 7, 24 is 6 times 4. So I can now see that common factor of 6. And we'll cancel that in a moment. When I have negative exponents in an expression, I always like to deal with those first. So the x to the 5, that's a positive exponent, so I'll leave it where it is. The x to the 3rd, that's a positive exponent, I'll leave that where it is. But to get rid of the negative 9 exponent, we can move that factor down to the denominator, and moving that across will change its exponent from negative to positive. After that, we can start doing some simplification. We could cancel those 6's off. So I'll do that. Could also combine these two pieces, so I'll do that. So I have the 7x to the 5th left on the top, have the 4 on the bottom, and these 3 x's plus those 9 x's would give us 12 x's all together on the bottom. And then I want to reduce the x's. I have x's on the top and the bottom. So the 12 x's on the bottom I'm going to write as 5 x's with 7 left over. These 5 plus those 7 give us those 12, but the reason I'm splitting it like that is so that you can see that these 5 cancel those 5 and there's 7 left over. You can do that without writing it out like this. A lot of times people will just say that right here to themselves, these 5, and they'll cancel them out, cancel 5 down here, and there's 7 left over. So that's an option too, is just to kind of do it like that. But this kind of shows clearly what it is you're canceling. And I think that's it for canceling. The 7 and the 4 have nothing in common. We only have x's on the bottom now. So 7 over 4x to the 7th would be our final answer on that one. All right, let's move on to simplifying the square root. 8 times the square root of 45. 45 is not a perfect square, meaning I can't think of an integer that if you square it gives me 45. So when that's the case, what you want to do is think, can I think of any perfect squares that go into 45? So perfect squares are 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, 7 squared, and so on. So I want to think, what's the biggest number in this list that goes into 45? And I think the answer to that question is the 9. So I'm going to rewrite that 45 as 9 times 5. So 9 times 5 is 45. And what's special about splitting this up is 9 is a perfect square. So I know the square root of it. The square root of 9 is 3. What's the square root of 5? Not a nice number, not any integer, so that one is stuck underneath. So because I split this up in a way so that one of the numbers underneath was a perfect square, I could ask myself the question, what's the square root of 9, and know the answer, which gets that out of the square root symbol. And then I can multiply these numbers out front together, 24. Don't know the square root of 5, none of these are a factor of 5. So that's just stuck in there, and that's my final answer. So I just want to point out again, it's not okay to just split this anyway. So like 45 is also 3 times 15, but neither 3 or 15 is in that list, so I don't know the square root of 3, I don't know the square root of 15, that's not useful. When you're simplifying the square root, you'll only want to split the number up if you can think of a way to split it up where at least one of the numbers is a perfect square, so that way you'll know the square root of it, and you can make some progress on simplifying that way. Alright, the next one looks like a half-life problem, so let's give it a read and a try. Scientists used a sample of spruce wood from some forest to date an advance of the continental ice sheet into some country during the last ice age. If 24.43% of the carbon-14 remains in the sample, when did the ice sheet advance? Assume the advance killed the tree. The half-life of carbon-14 is 5,730 years. Round the base of the exponential function to 6 decimal places and round your final answer to the nearest year. Alright, so the first thing I need to do is introduce a variable. So let's let t equal the number of years since the tree died or since the sheet advanced. Either of those would be the same, assuming the advance killed the tree. So since they're asking, let's look at their question, when did the ice sheet advance? So let's let t be the number of years since the ice sheet advanced. And then I'm going to set up a table where I have values of t that I put in and values of f of t that come out. So with these carbon-14 problems, we always do it with percentages as our output. So at year 0, which is kind of the moment the tree died, it's going to have all of its carbon-14. So a living thing has a balance of carbon-14 in it. Once it dies, there's, it's not kind of breathing, however a tree breathes, right? And it's not replenishing its carbon-14, so it starts decaying out. So at the moment it dies, it would be 100%, and then from then on it would be reduced. And because they say the half-life is 5,730 years, that means if we were to come back 5,730 years later, the amount of carbon-14 would be down to 50%. And we could do that one more time. If we take that 5,730 plus another 5,730, that'd be 11,460. Because that's another half-life, this would get cut in half again and would be down to 25%. And then we could use this chart to come up with our exponential decay function. So we put this stuff into L1 and the times, and we would put the percentages into L2, and then we can use exponential regression, L1, L2 to tell us the a and b for our exponential function, and we can write that out. So let's go ahead and take care of those steps. So I'm going to go to Stat and Edit. We've got some data there from before, so up arrow to highlight the list, clear, and down arrow will get rid of that data. Do that again, highlight the list, clear, and down arrow. Enter in these values of t. Enter in the values of f of t, whoops, different line. So 100%, 50%, 25%. And then go to Stat, Calc, down to 0, Exponential Regression, data in L1 and L2. Press Enter, and I get A, which is a nice number, and B, which is messy, so I'll round that to the 6 decimal places they asked us to. Let me double check that. Yep, 6. So f of t is equal to 100, the initial percentage of carbon-14, times 0.999879 raised to the t. So putting the 6 decimal places, noticing that that is below 1 because it's a decay. very close to 1 because this decays slowly. It takes 5,730 years before half of it's gone. So we're probably not losing very much each year. So it's just a very small difference between that number and 1. And then let's look at their question. They want to know if there's this much carbon-14 left, then how long has it been since it died? So they're saying solve for t if f of t is 24.43%. So that is a percentage, so it is an f of t, so that goes here. So 24.43% equals, and then we just copy the other side, 100 times the 999,879 raised to the t. And we're going to try and solve that for 100. I'm going to just make one quick change. This is 100%, but we didn't write the percentage symbol, so we should be consistent with that. And just go ahead and write a 24.43 right there, so I'll make that little adjustment. And now we want to try and solve for t. T is an exponent, so we're going to take a log at some point. First we're going to try and get the base by itself, so let's divide both sides by 100. And by the way, that step right there converts this percentage back to a decimal form, because dividing by 100 moves the decimal over 2 spots. So we get 0.2443 equals 0.999879 raised to the t. And I just want to point something out real quick. On a lot of other problems, I actually didn't carry out the division. I just left it as a fraction. It's okay to carry out the division if it goes nicely. So if it's messy, you're going to round, that brings an error. But dividing by 100 just moves the decimal over a couple spots, so that does not introduce any error. Okay, we have the base by itself. We want to get that t down. So if there was a log here, we could bring the t down. So we go ahead and put a log there, or take the log of this side. To keep this equation equal, we have to take the log of the other side as well. The reason we're doing that log is because then the t can get moved to the front, so that's what I'm going to do in the next step. So next line, we have log of 0.2443 equals, the t will move to the front. And then we want to solve for that t. So to get t by itself, we have to get rid of what's with it, which is this log, which is connected by multiplication. So if I divide right here by log of 0.999879, those will cancel, and t will be by itself. Got to keep the balance so that things remain equal. So divide the other side by the same amount. And then t will be by itself. It's just messy, so go to the calculator and approximate that. So they want us to round that to the nearest year. So to the calculator we go. So log of the 2443 divided by the log of that number, and make sure I ended parentheses on the first log and on the second. So we have rounded to the nearest year, 11,647 years, because the 6 gets rounded up because of the 8. So about 11,640 years since the ice sheet advanced. All right, moving on to number 8. The population of a country increased from 87 million in 1990 to 217 million in 2010. What is the absolute change? So when we're doing absolute change, we take the newer number minus the older number. So what are our years here? 90 and 2010. So we'll take the 2010 number first, 217, minus the 1990 number, which was 87. So we'll take the difference. You do that subtraction, you get 130. So the absolute change is 130 million, and million what? Dollars, feet? No, this was a population, so 130 million people. So the newer number minus the older number gives you the absolute change. For what is the relative change, you take your absolute change, which is 130, and then you divide that by the older number, which was the 1990 number, which was the 87. So that's typically going to be messy, so I'll bring in the calculator for that. 130 divided by 87. So like 1.4943, let's say. But then what are the units on that? So this is kind of a percentage, but it's in decimal form. So after we do the division, we want to put it in percentage form. So move the decimal 2 spots to the right and add the percentage symbol in. So this would be 149.43%. And then I think it's also important on these to talk about like what kind of change are you getting. So instead of just saying the change was 130 million people, what kind of change was it? Did it go up? Did it go down? Well, this is the older, that's the newer, it went up. So it'd be good to say this was an increase of, so let's expand that answer out, an increase of 130 million people. And that was an increase of 149.43%. And then fill in the blank. The population in 2010 was how many times as large as the population in 1990. So this is more than. So relative change tells you the population in 2010 was 149.43% more than it was in 1990. And to go from that more than idea to a multiplier, we have to take the more than amount, 149.43%, and then we have to add on 100%. So that takes us to 249.43%, and then we change that to a decimal by moving the decimal 2 spots to the left, and that gives us our multiplier. So 149.43% more than it used to be is the same as 2.4943 times as large as it used to be. So when you're going from how much of an increase you had to a multiplier, you have to remember to add the 100% in. All right, last question, number 9. Diners frequently add a 15% tip when charging a meal to a credit card. What is the price of the meal without the tip if the amount charged is $27.60? Label the unknown with a variable and solve using algebra. So when they say label the unknown with a variable, they're not just saying use a variable, but label what the variable means. So I'm going to let x equal the thing that we're trying to find. And what did they ask us for? What is the price of the meal without tip? So let's let x equal the price of the meal without tip. So now let's start thinking about some other pieces, like how much was the tip? Well, the tip, according to this, is 15%. So it would be 15% of whatever the price was before. So 15% of x. When you're doing math with percentages, you change them to a decimal. And of would be a multiplication. So we can just put that next to the x. So the tip is 0.15 times x. So when we go to put the amount on the credit card, what do we have to pay for? Well, we have to pay for the meal. So we're going to take that x, and then we're adding the tip on, so 0.15x, and then that's going to be equal to the total of what we pay, and they say that was $27.60. So there's our equation. We have to pay for the meal, which was x. We have to pay for the tip, which is 15% of that, and that gives us our total on the credit card bill of $27.60. And then from there, we just want to do straightforward algebra to solve. There's one little bit tricky piece, which is if there's no coefficient in front of the x, then that's a 1. So when you combine like terms, you add coefficients. So you have 1 plus 0.15. So that will be 1.15. Like if this said 8x and 3x, we'd say 11x, right? We would add those coefficients. So 1 plus 0.15 is 1.15. That's combining the terms. That's equal to the 2760. We're trying to get that x by itself, so we divide right here by 1.15 because the connection was multiplication. Do that on the other side as well. And then x is by itself, just a matter of what it is. So let's do the division. 27.60 divided by 1.15. Actually, I thought we would round. Usually we round. This turns out to be exact, so I don't need an approximately equal symbol because I'm not going to round, I'm not going to bring in error. So I can just put the 24. And then I should think about what the units are. That was $24. And I could go ahead and answer that and maybe a full sentence too. So the price of the meal without tip was $24. All right. Hope the video was helpful to you. Good luck on your test.